Good morning, good afternoon, good evening. Welcome to Late Night Learning. I am your host, Dr. Anthony Palomba. Today we're going to be getting more involved in cluster analysis. We're going to be talking about dendrograms and wrapping up that lecture. But first and foremost, I want to announce that this is the 100th episode of Late Night Learning. I cannot believe that I got here. I can remember way back in the fall of 17. December, November, October of 17, talking to Keith Baker here at Late Night Learning, even summer of 17, saying, oh, I've got to get into the studio, and I want to start recording lectures. And, you know, I never really thought that this would be something that would be a part of my life, something that really makes me excited every time I get to come to the studio and record stuff. It's been an absolute pleasure. It's been an absolute honor, and I hope to keep this going as much as I can. It has helped me with job interviews. It has helped me in talking to PR firms. It has been such a wonderful extension of who I am and what I believe in. I'm very passionate about educating, very passionate about talking in general, and so it's been a real blessing to have that merging together and to have this studio as my own for 2 years plus now, as I've labored to really build up this YouTube channel to really serve only one purpose: to educate people and to be able to do it in a way that's portable and mobile and hopefully entertaining. And so I want to thank everyone who's been a part of this. Thank you, Jim. Thank you, Dennis. Thank you, Keith. Thank you, everyone who has allowed me to come in here and to record these lectures. Thank you to White Plains Public Access Television in Westchester County, New York, for allowing me to be able to do this, to be airing these shows on public access television. And for those of you who watch, you know, I don't get to meet everyone, but I do get emails, I do get messages. Please message me. I do respond on my channel, and I've been lucky to have people reach out to me on YouTube from Florida and from all across this great country who just kind of bump into my videos and are thrilled with them and really enjoy them. And so, you know, I do this for the people as much as I do this for myself. I get great pleasure out of speaking about these particular topics, and if you're able to walk away with anything, it's meaningful to me. I think sometimes, you know, we wonder what our purpose is on this planet, and, you know, every day I still wonder what I'm going to be doing in the future. But this show gives me such great pleasure. I know when Keith edits this. I know when Dennis helps record this. I know when Jim gives the final approval. You know, it's going to someone who needs it, whether it's my students or whether it's somebody on YouTube who, you know, maybe is having a bad day or doesn't understand a topic or, you know, needs further supplemental education, you know, surrounding a particular topic. And so I am just so grateful to be here, and please keep watching. I get great pleasure out of doing this, and I want to keep this train moving along. So thank you guys very much. And so without further ado, let's get started. And so in the last lecture, we were talking about dendrograms, and we were talking about getting a better sense of what a cluster analysis can do for us. We know it helps group. We know it helps organize. We know that we have centroids, which are important because they help determine means of the clusters themselves. And so here I've run a k-means cluster analysis here just to give you a sense of what the output might look like on SPSS. Let's keep going. And so here you can see, just to give you a sense of how to do this, if you have SPSS up, you can see here that I have classify and then the k-means cluster. And I apologize that this photo isn't clearer. It was clearer in the PowerPoint deck, but sometimes the transition between certain software inhibits it a bit. But what I can tell you is that you can see here we have analyze, which is at the top bar. I've gone down to classify, and then that's opened up to k-means cluster. You can see above it two-step cluster and below it hierarchical cluster. You can see variables in the other chart box right here, all of those lists. And so this is a list of things people do. So it's people, you know, collecting coins and people gardening and people reading magazines to try to get a sense of what people do. Let's keep going. Cluster activities. So your initial cluster output will show you how many iterations will occur, average values for the cluster, and iteration history. So here we can see a few things. So in cluster 1, people really are not collecting coins, which is the third from the top. People are not really investing in the stock market, and people are not painting as much, right? So if we go to column 1, the first cluster, we know that these traits are on a scale of 1 to 5. And so 1 being low, 5 being high, we know that in cluster 1, a 1 for painting or playing a musical instrument means you're probably not creative or interested in creative engagement for that matter. However, if we go to cluster 3, we can see people are really into music and painting. People in this cluster really like making things out of wood, metal, and glass. People like collecting stamps and coins and things like that. So again, all of a sudden, we're seeing that there are people who fluctuate between activities. And so this is part of a lifestyle scale that I used in a study looking at movie platform and movie genre consumption and seeing how psychographics, lifestyles, and demographics could be useful in predicting this kind of consumption behavior. And so what we can see here is that yes, in fact, different kinds of clusters are produced here. Different kinds of clusters are produced here, which is very, very valuable because now we're seeing breaks, right? Now we're seeing initial cluster centers. Let's keep going. Iteration history. This tells us the differences change over time in the cluster iteration. So iteration is useful in how many iterations had to be performed. So 6.447 iterations for cluster 1, cluster 2, 7, cluster 3, 5, cluster 4, 5, 5.8, and cluster 5, 4.5. So you can see that there are, the clustering iteration slows down after a while. So we had 10 iterations here, 10 runs to determine which clusters were most homogeneous within and created the most amount of heterogeneity between different clusters here. Let's keep going. Cluster membership here. So with cluster membership, if you were interested, cluster membership allows us to look at the case numbers. Case numbers are people, by the way. So you can see participant 1 who took your survey, participant 2 who took your survey, or visited your social media feed, or visited your website, or whatever it may be. You can see who belongs in what cluster. And so this is useful information if you have to get rid of participants in particular, if you have to delete participants, if you want to get a better sense of the population per cluster. We kind of want similar populations in the clusters. We don't want one cluster to be 35%, one to be 15%, one to be 3%. It's probably not good. We want some sort of equal populations there that provide more comparison across particular clusters, so it's very useful to have that. Let's keep going. Final cluster centers. Final cluster centers are what you would be interested in if you wanted to go further. So we can see here there's a bit more, a bit less variation here. Here we're seeing tighter clusters here. We see with number 1, yeah, we still don't have people that are as interested in, painting, playing an instrument, or, working on metal, wood, and glass, or collecting coins as a hobby, or investing in and keeping up with the stock market. But there's more equalness within the group, right? There's less variation within the group, and we can kind of see this. If you look at cluster 5, it's very, very similar there as well. We have a lot of people who have similar affiliations with different kinds of lifestyle activities. Let's keep going. Distances between final cluster centers. So you want to ensure there's enough heterogeneity between clusters. This is really, really useful to ensure that. You can see the distances here. And so it's useful to see how far different clusters are from each other. And so for the first cluster, we can see 3.886, 4.638, 3.887, and then 9. So it seems like cluster 5 and 1 are super far from each other relative to 2, 3, and 4. And that is the way to be able to read this particular chart. You want to compare the numerical means here, or distances, if you will, which are relative. So 3, 4, and 3 in the first column, 3.8, 4.6, and 3.8, those are relatively similar numbers compared to 9.014. And so from there, you get a sense of where true distance lies between these clusters. So it looks like everyone broke out pretty well, though I am curious why 1 and 5 have such differences between each other. That might be a problem. It might be cause for me to further investigate here. Let's keep going. ANOVA table. Can't get away from the ANOVA table. Here, in a cluster analysis, an ANOVA table will instruct you surrounding whether or not each variable was useful in determining cluster output. So the goal here is to have each variable be statistically significant here in creating each cluster profile. And as we can see here, each variable here, or really each indicator is what I should be stating here, is significant. Each one was instrumental in the cluster analysis. If some aren't statistically significant, and again, we look at statistical significance in the rightmost column here, the SIG column. We want to make sure that the SIG numbers are 0.05 or less. And here we have 0.000, although we know there's no such thing. It's 0.00001. Can't have perfect, you can't eliminate error here. And so it makes sense to have 0.0001, but SPSS tends to just round. So just bear that in mind. Anyway, we look at the SIG column, 0.05 or less. The chance of this particular pattern being due to random chance is 0.05 or 5% or less. That's what we look for. That's the threshold in the social sciences. It is arbitrary, as we've gone over before, but it's something that most researchers have consensus over. We can see here that each indicator is statistically significant. Each one registers as super important in this cluster analysis. Now, in the SIG column, if we had something that said 0.15 or 0.25 or 0.35, we could eliminate it and rerun the cluster analysis to see if we get better breaks, better clustering as a result of getting rid of that indicator. Let's keep going. Cases in each cluster. This just tells you the population. Population in cluster 1, 65, 2, 108, etc., etc. It's just a quick way to look at, is everything breaking pretty well? For the most part here, it looks so. I'm not sure what happened with cluster 1, but again, I'm also not terribly alarmed here. There just seems to be a pretty good break between each cluster here. Let's keep going. Producing k-means cluster membership. Remember, if you want to create clusters for further analyses, you want to be sure that you create a cluster membership. That's important to be able to do here. Let's keep going. And then a new cluster coding scheme will be produced. You just have to view it in variable view, but you'll see that something new has been created here. Let's keep going. Measuring dissimilarity between clusters. So you may need to measure how dissimilar clusters are because you want to make sure that there is enough heterogeneity. So complete linkage clustering. This computes all pairwise dissimilarities. It considers the largest value of dissimilarities as the distance between clusters. So in other words, it produces less tight clusters. Again, this is up to you. You have to determine how tight you want your clusters to be. Single linkage clustering, this computes all pairwise dissimilarities between the elements. It considers the smallest of these dissimilarities as linkage criterion, again producing less tight clusters. Mean average linkage clustering, computes all pairwise dissimilarities, and it considers the average of these dissimilarities. And then centroid linkage clustering, it computes the dissimilarity between the centroid for cluster 1 and for cluster 2. And then we have Ward's minimum variance method. It minimizes the total within cluster variance. At each step, the pair of clusters with minimum between cluster distance are merged. It's like kind of splitting hairs when you get into this, to be truthful with you. I want you to be aware that there are different ways to link clusters together. That's all. When you're going through your options, you can leave it on as standard for the most part. If you really have a reason why you need to deviate from the standard, whatever's been checked off already by SPSS, do so. But this is something just to be mindful of. There are different ways in which you can measure distances between clusters. But again, you can just simply use what SPSS has already checked off. It already has things preloaded, and really you can just go from there. Well, that's all the time we have on Late Night Learning. Again, thank you so much for watching. Thank you so much for being a part of this. I'm so happy that is the 100th episode. I've got my birthday coming up this week as well. It's been a very, very good week. As always, keep laughing and keep learning, and let's go for another 100. Thank you, guys.